so today we're going to be talking about centrifugal pumps. There's two different types of pumps, but in intro I tend to elaborate on centrifugal because they're the more common equipment. We'll go over PTEC pumps versus centrifugal and elaborate on those, okay? So what a pump does, regardless of the type, it's going to move liquids by increasing their pressure, okay? Y'all can fill out y'all's booklets later with this. Does that work? Because I'd rather y'all paying attention and grasping and understand the concept versus, yes, I'll fill it in with y'all, okay? Fair? All right. Okay, so who knows how your washing machine drains? Like, how do you get the liquid out of the washing machine once it's in there? A pump. Yep, I actually, on my 30th birthday, my washing machine quit draining. And this was before I was married, but climbing back and forth, back and forth. It ended up being a bobby pin stuck in my little centrifugal pump. But that saved me how much money? Calling someone out, just being able to, well, it's the pump. Let's find a diagram, figure out where the pump is and how to get to it, right? Probably $500. How does fuel get to the engine of your car? Gasoline. How does it get there? Fuel pump. Water well at home. Does anyone have a water well? You have a submerged pump that's supplying the water. And okay, so centrifugal force is from the center out in a circular motion. Okay, understand that? From the center out in a circular motion. Most people will just memorize that, so I'm going to give you a visual, okay? From the center out in a circular motion. Alright, so what is centrifugal force? What is it? From the center out in a, is it a square motion? No, is it from the outside in? No. What, so what kind of force was making them fly out? Centrifugal, see someone hold a 5-gallon bucket that's full of water, and if you just sit there and do like this, it stays? Centrifugal force, holding it in. Okay, so how do you think a centrifugal pump makes a liquid move? It slings it from the center out in a circular motion. Yep. Section I, your liquid's getting pulled in. Your impeller is spinning. It's slinging it from the center out in a circular motion. Centrifugal pump uses centrifugal force to move the liquids. Moves liquids by increasing the pressure of the liquid, right? Your suction, think sucking it in, you're pulling it, right? So your suction is going to be your inlet. Your discharge, think, what's it called when you're leaving the hospital and they're giving you all your papers? Discharge. You're getting discharged from the hospital, yeah. So discharge, think outlet. You're leaving. It's leaving, right? Your pipe diameter, the way you'll always be able to tell, don't think that all centrifugal pumps have the suction, or all rotating pumps have the suction on the side and the discharge coming up. You do have parallel pumps or vertical pumps, however you want to say it, where suction, discharge. Most of them are going to be designed like this. But you'll always be able to tell which one the suction is and which one the discharge is based on pipe diameter. Smaller pipe diameter means higher pressure. Because when you compress something, right? We're not compressing these liquids, I'm not saying that, but when you compress something, you make it take up less volume, right? higher pressure, higher pressure, lower pressure, higher pressure, smaller pipe diameter. Okay. So your pump casing is what looks like a snail shell. You're going to have your shaft, which is connected to your impeller. This is a closed type impeller. They have closed, it's on the next slide, but they have closed, partially open, and open. And then your shaft is going to be connected to that impeller, making it rotate. So this is a semi-closed impeller or semi-open. This right here is your shaft and your shaft pin connecting it to your impeller. And these are your different types: open, semi-closed, closed. Okay? So your bearings, these are your ball bearings, and I'm going to pass them around. We used to have a broke one and I can't find it. So there's actually balls in it. The inside part would be attached to the shaft. It would be sized according to your shaft. The outside is actually going to be attached to your bearing housing, okay? And what it's going to do is allow the shaft to spin while holding it steady, okay? So this is a different type. This isn't going to, well, yeah, this is a different type, but it's the same concept. This would be attached to your shaft so it can spin. This would be attached to your pump casing, and this one you can actually see the little bearings. Usually it's going to be ball bearings like this though, with little balls in it, okay? So you actually have thrust bearings or axial and radial bearings. Your radial bearings are going to prevent your shaft from doing this, up and down and side to side. Your thrust bearings are going to prevent it, or axial bearings are going to prevent it from going forward and backwards. You don't want your shaft moving with all that weight on the end of it, right? So, just to kind of show you, and that's just a close-up zoomed in, and of course, that's a cutout of it, of the sleeve that's attached to the bearing housing. Yeah, good? Let me make sure there's nothing else in this video. So your bearing housing, you'll always be able to identify it because it's going to have some kind of oil system. Anytime you have rotating metal parts, you're going to need lubrication, right? So your bearing housing, and I'll show you on the next slide, but you'll be able to identify it. See this right here? This is an oil level sight glass. Or you'll have your tripod oiler, which is right here, showing you the oil indication. This is where your oil is going to be for your bearings, okay? It's going to actually be deep into the bearing housing, and your balls for your bearings are going to be dipping in it. Not fully in it, but dipping in it, and it's going to be dragging it around. Okay, so minimums where just the tip of the ball is getting in, max about halfway. Okay, so as it rotates, and I'll show you all this in the equipment room, as it rotates, it's going to be dipping into it, okay? Making sense? Follow me so far? Okay, so this is a real life pump. We only have cutouts, but this is what one would look like in your unit. This would be your bearing housing right here, okay? Following? All right, so that is your oiler, or your oil level indication. It's hard to see a little bit, but. Okay, so who makes the wheels on a car spin? Is it the baby in the back seat? Is it the backseat wife driver? No, who is it? Who? Not what?
Oh,
The driver? Yeah, you're right. I was talking to him when I was correct. All right, so whatever's making the impeller spin on a pump or compressor or a generator is going to be your driver. You have electric motors and you have steam turbines. There's different types. The most common you're going to come in contact with in the local industry is going to be an electric motor or a steam turbine. So you see how its shaft is connecting to the snail shell, which is the pump. Same concept, it's shaft. This is the steam turbine. It's connecting to the snail shell, which is this pump. Okay? And we're going to go outside and look at that one later. Okay, so how do we connect the driver and the pump together, right? There's a shaft that's connected to our driver. There's a shaft that's connected to our pump. Okay? Let's see. And this isn't exactly how they connect, but just to give you an idea of how coupling works. So you have your driving shaft, right? It's rotating because the motor's rotating. And once they connected, now you have your driven shaft, which is your pump or your compressor that's being driven. Now it's rotating. Disconnect, well, nothing's happening. So this is just a visual of a coupling. These are different types of couplings. And I have a video of, well, I thought I did. Oh, it's at the end of that video. Hold on, let's see. There we go. So this is the common type that we're going to have. So the sleeve goes on, it connects both of them, and now when one turns, the other turns. So the reason we don't just have two shafts welded together, this is our secondary defense system. If something happens where that pump is spinning backwards, we're going to get on that in a little bit, but something causing that pump to spin backwards while our driver is shut down, and then our driver kicks on, instead of damaging our driver and our pump and our shaft, that coupling should shred. It should eat the teeth off of it to where it disconnects. Now, that's in an ideal situation. They rust. They get stuck together from rusting, right? They corrode together. So, not always the case. Hopefully it is if you ever experience it though. Okay, so your coupling guard, according to OSHA, if you have something rotating, it's supposed to be covered at all times. That is not always the case. But this would be your coupling guard. This is where your two shafts connect, or your shaft guard. Depends on the plant you're at, what it's called. But your coupling is actually under there connecting your two shafts. Okay, so this is another example of real life where your coupling guard's going to be. Good? Snail shell, right? Snail shell. Driver's over here, driver's back here, or right here. Shaft is coming out right here. That's the shaft coupling guard, right? And then the shaft has to enter the pump casing, right? So it has to enter the pump casing, and it has to be able to rotate freely to make the impeller rotate, right? So how do we prevent, can we have two pieces of metal touching so tight that nothing leaks out while it's rotating thousands of RPMs? When I say RPMs, I mean rotations per minute. That's what it means. That is not what it stands for. It's revolutions per minute, but that's the trick, okay? So don't ever tell someone it stands for rotations per minute. It's revolution per minute, but in your head you can kind of use that as a trick. So can we have the pump casing and the shaft just touching so close that nothing leaks out? No, we can end up causing friction and damage and stuff, right? Can we weld our shaft to our pump casing so that way nothing leaks out? Would it be able to rotate? Could we bolt it or thread it to where would it be able to rotate if we did that? No. So what we have to prevent leaks out of where our shaft enters our pump casing, right? We gotta have something there to prevent leaks. We got seals, okay? Seals are always gonna be located where your shaft enters your pumps. I've said it like 16 times. The snail shell, the thing that's shaped like a snail shell. What is it called?
Pump case.
Pump casing. So it's always where your shaft enters your pump casing. Because we can't bolt it, weld it, thread it, or have the two pieces of metal so tight that nothing leaks out. We got to make sure that what's in the pump is not leaking out to the environment, right? All right. Okay, this is actually a really good video on seals.
That's why mechanical seals are replacing old methods day by day. since they are designed more and more to be efficient, which is projected to remedy these disadvantages. The most common mechanical seal has 3 sealing points. The stationary part is fixed to the back plate of the pump with a sealing basket between them. The rotating part, instead, fixed to the shaft with a seal between them as well. In this way, the rotating part rotates, is integral with the shaft. One of the 2 parts, in this case the rotating part, possesses one moving element that is firmly fixed and pushed from a spring. This one presses against the permanent part, creating the last sealing point. This moving element follows the shaft movements caused by the bearing gain, the misalignments caused by the production tolerances, and from thermal expansions during the functioning. The seal between the rotating and the stationary part is the element that the mechanical seals have in common. As you can guess, the 2 parts are in contact with each other, and the rotating one causes friction on the other during the rotation. For this reason, the faces of the 2 parts that are in contact are made of flat surfaces, worked with extreme precision and smoothness. Besides, the pressure inside the pump, combined with the centrifugal effect obtained from the rotating part rotation, cause a fluid film to be created between the faces in the contact, made from the same fluid.
Okay, so this split right here, this film, we call that a seal flush. Okay, it is going to be, you don't want these 2 touching, because if they're rubbing together, they're causing friction, and then they're going bad too soon. Okay, you want a gap in between yours. So the one attached, you have two seals. Okay, mechanical seals. You have the rotary and the stationary. Which one do you think is attached to the shaft? And which one do you think is attached to the pump casing? Or the seal? Yeah, the stationary, because it doesn't rotate, right? Does that make sense? Okay, so you don't want them rubbing together. It's going to cause friction and damage your seals. So you have your seal flush come in, and it's going to sweep it. So it lubricates it, not in like, it's not oil, but in a sense to where it prevents the friction, right? And it keeps it cool. And so how does it keep it cool? Well, it prevents the friction, right? And then also, what I mean by sweeps it is it's just steadily flowing through it. So if you have any like little piece of sand or something in there, remember that gap is one human hair. That's how wide it is. So if you get a little piece of sand or something there and it's spinning and it gets caught in there, well, it's going to eat your seals. So that's what this seal flush does. It keeps it cool, lubricates it, and prevents it sweeps it, keeps it clean. Clean, keeps it cool, and lubricates. Good? And I'm going to explain to y'all a little more how that works in a second.
With pump from the system, that while it lubricates them, also prevents direct contact. This lubrication foil can also be introduced from an external source. In this way, the mechanical seals can isolate the internal pump room.
That spring that I showed you earlier, that seal flush is coming in and putting resistance on that spring enough to make it the gap of the human hair. Without the seal flush, you're touching because you need such a tight fit, right? Good on that? Okay. There's a whole lot of seal plans, okay? I'm about to crop that out. Cut that out. All right. Seal plan 11 is one of the simplest, and it's very common, where we use, where's the highest pressure at on our pump? Is it going to be the inlet or the outlet? Outlet. The discharge, right? So what we're actually doing is we'll have a little tubing coming from our discharge. This is our shaft right here, okay? So this would be our suction discharge. Shaft is coming out right here. It's just cut. Our seals are always where our shaft enters are what? What is where the shaft enters the pump casing? All right. You always know if you have mechanical seals, you're gonna have a seal flush. If you have mechanical packing, If you have mechanical packing, you're not gonna have a seal flush. So mechanical packing, I'll pass this around, it's just a braided rope, okay? It would go where the shaft enters the pump casing, but that is only if it is a non-hazardous material, like a water system. You could use mechanical packing. It's not as effective or efficient. It's likely to leak. The only times that you would have it where it's not, where it is a hazardous system or process fluid and still have packing is if it's a very, very old plant and they don't have the updated pumps or technology. So if it's a 100-year-old plant, okay, so I'm going to go ahead and show y'all seal plan 11. So your flow is coming from your discharge. Doesn't actually show it, but it's going through the flush, or going through between your two seals, and then coming back, and it's getting pulled into the suction eye. So it's just recirculating your process. And then your seals have a housing around it to prevent that from coming out. But it should be the higher pressures coming in, and then the suction eye is the lowest pressure. It's almost a negative pressure pulling it in. So it shouldn't be pushed out, if that makes sense. Plan 14. Like I said, these plans go like 1A, B, C, D, E, F, G, like, so there, and it goes all the way up. And then next number, next number, next number. There's hundreds of them. So this one's coming from the discharge, and then it actually goes back into the suction instead of back in right here. It would be going through this. Your rotary and your stationary. Okay, so let's do a recap. Where's our driver at?
Right on the left side.
Let's see if my driver?
Yes.
Alright, what's this?
Shaft cover.
Shaft and coupling guard? Alright, what's this? What's that? That is a level indicator. Also, another way you're gonna always be able to identify your bearing housing, you're gonna have a vent, you're gonna have a fitting plug that's on a high point, which would be a vent, and you're gonna have a plug at the bottom, which would be your drain. That way you can, maybe not you, it depends on the plant you work at, if maintenance or if you are gonna be the one changing the oil in your bearing housing. But that way if you get water in your oil or something like that, you can drain it and replace it. So what is it? Bearing housing? Alright, what about right here? What would that be? That's where the shaft enters the casing, so what would that be? Right
Seals.
Here? Seals, and then what about this little tubing right here? Seal flush. So what kind of, is it mechanical seals or mechanical packing?
Mechanical seals.
Because you have a seal flush.
Seal flush.
Okay, does that make sense? Where's our suction at? Is suction higher pressure or lower pressure? Suction the inlet or the outlet?
Inlet.
The suction, you suck something out or you suck something in? Suck it in. Alright, so is that our inlet or our outlet? Alright, is that going to be higher pressure or lower pressure? Lower, because the purpose of the pump is to increase the pressure, right? Alright, so which one of these would be our suction? Or this one? A or B? Alright, which one's our discharge? B. Okay. Good? Yep. Alright, so this is a steam turbine. It's going to be our driver. We have our inboard seals and bearing housing for our turbine. We're going to have our coupling guard or shaft guard, depending on the plant you work at, what it's going to be called. Then we have our bearing housing, and you can tell it's the bearing housing because you're always going to have a vent plug, and then you're going to have a drain plug down here, and then also it's on the other side. This right here is your oil level gauge or indication. So it's a sight glass to show you your level. This is where you're gonna have level at. And then from there we have our seal housing. You're gonna check for seal leaks down here below the seals. On this side, I know I'm moving too much, but bear with me. This is gonna be your seal flush. You know it's a seal flush because it's tubing that is going to your seals. So we automatically know that this is mechanical seals inside this pump. If it was mechanical packing, it would not have a seal flush. This is the simple plan 11 that I showed y'all earlier. This is gonna be your pump casing. It's the snail shell. And then this would be your suction line. This would be your discharge line. And we can tell because the smaller pipe diameter is going to be the higher pressure side and your discharge is going to be higher pressure.